Today's notes are about applications of electric fields, and this year we really skipped a lot about electric fields. But we can use what we know about Coulomb's law and work and potential energy to make this make sense when it comes to charges. So the first thing I want you to know about is that anytime you separate charges and put them where they don't want to be, you're actually giving charges potential energy. So letter A is actually just giving an analogy, right, to gravitational potential energy. Just like when you put a ball up higher in the air, you give it more energy. That would be like separating a positive from a negative, because those two are attracted to each other. And so when you separate those two, you have to do work to separate those charges. And so doing that work and then holding them there, let's say, doing that work gives those charges electric potential energy. And there's this diagram here showing that analogy. And here I was labeling this big charge, big Q, and the little positive one with a little q. Up until now, we've been talking about QA and QB. And sometimes when we talk about electric fields, we're talking about the fact that if there's a really large charge, like the whole area around it is affected. Just like if there was a planet, everything around it is affected by its gravity. So when we talk about electric potential difference, really what that term means is the work done on a charge divided by how big that charge is. And we can go into why we're doing this instead of just using work. Like, why don't we just talk about the work? Okay, well, the reason is that often we get lazy and it's hard to count exactly how many coulombs have gone by, and how much charge has moved. Sometimes we do that, but sometimes we don't. So we kind of just take just give me the joules per coulomb, give me the average amount of work per coulomb that's getting done in this situation. And so that is a concept we use when we talk about electricity, is this electric potential difference, which is given as a work done per coulomb. And remember that work can be a change in any kind of energy. So here we're talking about like electrical potential energy. We would need, in order to solve for this formula, we would need to know the work done on the charge, how much charge we did work on, and then you can use joules per coulomb, or you can, the nickname for this is volts. Okay, the electric potential differences can be negative, so sometimes you can get negative readings, just like you could have a negative potential energy if you went lower than the 0 level. Okay, and then when we talk about electric potential difference, that is also known as voltage. People just probably got sick of that long name, and they started to call it by its units. Okay, so you can see here, though, that with two things that attract, the potential energy or the voltage is higher when they're farther apart, because you're kind of separating them where they don't want to be, and the farther they get apart, the more potential they have, right? Because they would like to be together. The opposite is true when you have like charges, because they don't want to be close together. They want to be as far apart as possible. And so that's why you have very high voltage, high potential energy when they're closer together, which is interesting to think about. Okay, so we're going to do a really quick example problem. related to work and charge and voltage. So here they tell us how much this car battery is. So this is going to be our voltage. This is every car battery, right? Actually, they may look different, but that's a standard. So your car battery is 12 volts. And then this is our Q here, or I think in the formula it's got a little apostrophe, so it's called Q prime. It's 1.44 times 10 to the 6th coulombs. That's a lot of charge, okay, so that your battery could last a long time. Okay, so we're going to try to find the work using our new formula. And so when we do this, we're going to plug in what we know, and then we're going to multiply both sides by the amount of charge. So then we get a huge number, right? So let's do 1 point. Now we're going to round this to 2 sig figs, I guess. 1.7 times 10 to the 7th. And remember, a volt is really a joule per coulomb, right? So then when I multiply both sides by coulombs, I'm going to be back at joules, which is a unit of work. Okay, so that's a lot of work, which means you could probably leave your car on for a long time, hopefully, before the battery goes dead. Okay, so that's it for this little section of notes.